Chapter 19, the first law of thermodynamics. We have previously studied energy, but was limited to mechanical energy, things like kinetic energy, potential energy of a gravitational or elastic nature, and so on. But we know there are more forms of energy than those. For example, there's electrical energy, there is magnetic energy, and in our case, energy associated with temperature change. Common sense tells us that if we heat something up, like put this kettle of water on the stove, we heat it up, energy is introduced into the water, making its temperature higher, right? So when it comes to energy associated with temperature change, how do you balance energy? What is the conservation of energy involving heat exchange and change in the energy associated with temperature? That is discussed in the so-called first law of thermodynamics. Now, to understand the first law, we have to introduce a couple of new concepts. One is called internal energy, and the other is heat. When it comes to kinetic energy, it's the energy of motion, right? And potential energy, for example, the gravitational potential energy has to do with the conservative force called the gravitational force, and specifically, it depends on where you position this object in the gravitational field. The higher it goes from the ground, the greater the gravitational potential energy, and so on. But now let's consider this kettle of water. I can take the entire kettle and move it from the first floor to the second floor, and in doing so, certainly there is an increase in the gravitational potential energy of the water, or even the entire kettle as a whole, right? But we have seen that before. And we can also grab that kettle and remove it from place to place. So the entire kettle, including the water inside, is in motion, and it's got kinetic energy as a whole. But these are not things that we're concerned about at this point. Let's consider the case of the kettle sitting on a stove, and we heat it up, like you see in this depiction. There is no change in the vertical position of the kettle. There is no movement of the kettle as a whole. But as you heat up the water inside, the temperature goes up. There is certainly an energy exchange. And as a result, the temperature goes higher. What kind of energy has increased inside the kettle? We look at this water. Well, it turns out it's not the entire kettle moving or the entire kinetic energy of the whole piece or the potential energy of the kettle, but rather you have to go down to the molecular level. Okay, you have to look at what happens if you think of the this kettle of water as a whole bunch of water molecules. Right? Consider it as a whole bunch of water molecules. You have this water molecule here, a huge amount of water molecules. All these molecules are in motion. Right? They move. And as they move, each of them has a little bit of kinetic energy, a tiny bit, but there are a whole lot of them, so you can add all these energies up. That's a sizable amount. And common sense tells us that if you heat up the water, you can expect these molecules to move faster because each, on average, receive energy and they can move faster. Okay, so we're talking about molecular kinetic energy, the energy of the kinetic energy of each molecules. And on top of that, we also have potential energy because the molecules interact with each other. Right? They attract or repel each other, and the force between them is electrical in nature, and that is a conservative force. So we can introduce also the potential energy associated with the intermolecular force. So when we add all the molecular level or atomic level energies of the water in the kettle up, okay, we have molecular kinetic energy, molecular potential energy, or even you dig deeper, look at the atomic level, not the molecular level. There are also more energies available. When you add all these energies at the microscopic level, you add them all up, you get yourself what's called internal energy. Okay, so internal energy is the sum of all the energies of a thermodynamic system at the microscopic level, molecules and atoms and so on. And it has to do with temperature. It has to do with the state of the matter, such as whether this water is in liquid state or solid state, or in steam. Makes a difference. Now you see, as we heat up the water more, at some point it's going to boil and steam is created. So giving it extra amount of heat can bring the water from the liquid state to the gas state. So clearly, it makes sense to imagine the gas state contains more energy if the temperature is the same. Okay, so that's called internal energy. And how does one change the internal energy? Well, there are multiple ways to do that. And the way that's depicted in this picture is you heat it up on the stove. Okay, when you do so, energy flows from the flame in the stove into the water in the kettle. So there's a flow of energy across the border of this system, which in this case is the water in the kettle. It moved across the kettle into the water inside, and that transfer of energy, okay, is called heat. Okay? So heat is not the same as internal energy. It is a transfer of energy into a thermodynamic system from one system to another, which can change the internal energy. So that is called heat. Okay. So make sure you understand the difference between these two. And internal energy, we typically use the symbol of E, internal. And the amount of heat that enters the system is called Q. So if there's nothing else going on, okay, if heat transfer is the only way to change the internal energy, then they would be equal, won't they? That is the conservation of energy at work, right? If 10 joules of heat is transferred from the flame into the kettle, then the internal energy of the kettle has increased by 10 joules. But it turns out there are other means to change the internal energy besides giving it some heat. So we can have to add some ... here. And you will see that later in this chapter to complete the mathematical expression of the first law of thermodynamics. But we're already starting to do that here. All right, let's see here. Heat is energy transfer. So the unit of heat, of course, is the same as unit of energy. So that's joules, right? That's the SI, standard SI unit. But traditionally, there's also a unit we use for heat that's called calorie. By the way, sometimes we have capital calorie or 1 capital C, and that is defined as 1,000 small calories, okay? The small calorie, the C is not capitalized, okay? And the food industry, when they say calorie, they say, this hamburger is 500 calories. They mean the capital calorie, okay? They mean the big calorie with capital C, all right? Otherwise, they don't scare you into giving you a big number, but actually that's what they mean, the capital. Okay, and there are some other units that we often use, such as the British thermal unit, BTU, right? BTU. Both the calorie and the BTU are related to heating up water. How is 1 small calorie defined? Well, we take 1 gram of water, right? And we give it some heat to increase its temperature by 1 degree. Okay, it's actually not just from one temperature to another temperature a degree higher. It has to be between 2 specific temperatures that differ by 1 degree Celsius. It's a very specific temperature, but roughly speaking, between 0 and 100 degrees Celsius, it doesn't change by much. So basically, we just take 1 gram of water, we heat it up so that its temperature goes up by 1 degree Celsius, or 1 Celsius degree. Then we say how much heat is needed to accomplish that. That amount of heat is called 1 calorie. Okay, 1 calorie. What about BTU? BTU has to do also with heating up water. It's the shorthand British thermal unit, BTU. And so basically what you do is you take 1 pound of water, okay, a little bit more, right? Actually, a whole lot more than one gram of water. You take 1 pound of water and you heat it up from 63 Fahrenheit degrees to 63 degrees Fahrenheit to 64 degrees Fahrenheit. So you increase the temperature by 1 Fahrenheit degree between these two numbers. If the amount of water is 1 pound, how much heat is needed? That is called 1 BTU. Okay. So these units are different. They all represent proper units of heat. How do they transfer from one to another? Well, actually, a more fundamental question we should be asking before that is, is the transfer of heat really a transfer of energy? Of course, we know by now this certainly is the case, but it wasn't clear to people in the past. As a matter of fact, somebody had to come in and convince the rest of us that heat is actually a form of energy. When you put something on the stove and you turn on the stove, and then heat from the flame will enter the water to make its temperature higher. In the past, people thought there was an invisible substance, the so-called essence of heat, that can bring up the temperature. It went from the flame into the water in the stove. They didn't realize it was just a flow of energy. Okay, it was not a mysterious substance. It's just a flow of energy, but it wasn't immediately clear to people until somebody solved that issue, and in fact even did an experiment to convince the rest of us that calorie and joules actually this is a form of energy we're talking about. And this experiment was done by the great British physicist James Prescott Joule, and in fact, this is how he earned his unit, right? Joule is an SI unit of energy named after him, and he was the person who convinced us that heat was a form of energy. And this experiment allows you to find the conversion between 1 joule and 1 calorie. Okay? You know what calorie is, right? The way it's defined, you have to heat up, you have to increase the temperature of water, right? But joule has to do with the work, right? It's a mechanical work initially. That's how we measure 1 joule. You use 1 Newton of force, push something by 1 meter, and the work that you just did was 1 joule. So can we bring up the temperature of water by doing mechanical work instead of heating it? If you can, then achieve the same result as heating it up, which means the heating process is the same as doing mechanical work to the water, which means it brings energy to the system, right? So this experiment, here's the device. So what you have here is a chamber of water, and there is it's thermally insulated to prevent energy from escaping. Now, there is a falling object, okay, which is attached to an axle, which can turn a rotating paddle. So as this thing falls, as the block falls, gravity does work on the block. Okay, the block loses potential energy, but in turn, it causes the axle to turn, and therefore it turns the paddle, and the paddle then stirs the water. As we know, that can gradually bring up the temperature of water. Okay? In doing so, how much, assuming there's no energy loss, okay, how much work is done by gravity? If it goes down by an amount h, I would have mgh, right? Mgh. And what did that become? That becomes the energy absorbed by the water to change its temperature. Okay. Now, if this turns out to be temperature energy needed to bring up 1 gram of water by 1 degree Celsius, or by 1 Celsius degree, then this is 1 calorie by definition. Okay, all we have to do is find what that mass is. We know what G is, and then we find what that H is, and that side, of course, is in joules. So that gives a conversion between joule and calorie. And if you do this experiment carefully, you find the ratio to be 4.183. That is the conversion between joule and calorie. Okay, I'm sorry, the other side is calorie. So not only do we realize now that heat is a form of energy, like in this experiment, giving it heat has the same result as stirring the water, doing mechanical energy to it. They can both increase the temperature of the water. We also realized that there is a quantitative conversion ratio between 1 calorie and 1 joule. Okay, 1 calorie is roughly equal to 4 joules, or 4.183 joules for to be exact. This is called the mechanical equivalent of heat. Okay. Now, knowing the conversion ratio, we can do a little interesting estimation. We all know that if you want to lose weight, you have to control your appetite. You cannot eat too much, right? But what are the numbers? What are the numbers? Let's look at a typical case. Let's say you went to a restaurant and you ate a hamburger. When you wonder, how much work do I have to do? How much workout do I have to do in the gym in order to burn off all these calories that I just took in with the hamburger? Let's do a little estimation, shall we? See if the numbers add up. Now, hamburgers do not come in the same amount of calories. The rule of thumb is that the greater amount of calories, the tastier it is. And also the bigger the portion, of course, because to be tasty, you need fat and cholesterol, all these things, and they all carry some energy content. They have extra calories. So let's say you're health conscientious. Okay, you didn't go for that 1,000 calorie huge burger. You went for a small one, only 200 calories. It's a very lean hamburger. Okay. Very lean hamburger, but by the way, this is 2,000 big ones. Okay, that's what the food industry always uses. They don't use small calories. So that actually is 200,000 small calories, which is roughly how many joules? Remember, 1 calorie is about 4 joules roughly. So this is 800,000 joules. Wow, just a small lean hamburger. It doesn't taste that good. I tell you, if it's that lean. But nonetheless, you say, okay, I'm going to go to the gym. I'm going to burn this off. Okay, I'm going to do some weightlifting. Say, all right, you go to the gym, and you start doing weightlifting. You ask yourself, how many weightliftings do I have to do in order to burn off these 800,000 joules that I shouldn't be eating? Okay, so let's see. Let's do that. The amount of work that you do to increase the potential energy of the weights of mass M by an amount H is mgh. Okay, mg is the weight that you lifted. H is the vertical distance that you weight this thing, that you lift this thing. Okay, so let's see here. Let's say you lift something pretty heavy, 100 pounds. Okay, that's not all that small at all. 100 pounds. That's roughly about 50 kilograms of mass. Okay, roughly about 50 kilograms of mass. So M is roughly 50 kilograms. So 50 times G is about 10 or 9.8 times H. H is basically extend your arms and over your head. How much higher does the mass go up? Let's about a meter. Okay, about a meter. So looking at 500 joules per lift. Wow, you put this much effort into one lift, 100 pounds, lifting over a vertical distance of 1 meter. You only did 500 joules of work. Really? If that's the case, how many repetitions do you have to do to just burn off this lean hamburger? The number N would be the total amount of calories or joules you have to burn divided by what? Divided by the amount of energy you burn per lift, which is 500 joules. Wow. That is remarkable, isn't it? We're looking at 800,000, right? Divided by 500. Let's see what we come up with. 1,600 lifts. Can you believe that? Did you ever go to the gym once and did 1,600 weight lifts? No way, not even close, right? And that is only to burn a 200 calorie, very lean hamburger. What does that tell you? It seems that these numbers do not add up at all. I mean, if you believe these numbers, then basically the conclusion is, don't go to the gym. It's totally useless. It's a waste of your money and waste of time. The only thing that you should do to keep yourself lean, to keep yourself from gaining extra weights is to not eat that hamburger, right? Even lean hamburger can do this much damage, right? To your weight control, right? Okay, now this is a little weird, don't you think? It doesn't agree with our common sense. We all know that going to the gym is actually good for you and so on. So what did we do wrong? I mean, numbers do not lie, right? What did we do wrong? What do you think? Well, you can pause the video here and think about it a little bit. Okay. What do you think about it? Did we forget something in our estimation of these numbers? Well, clearly it's 800,000, 800,000 joules. There's nothing we can do about that, right? But when you go to the gym and you start doing weightlifting, every time you lift this weight of 100 pounds over your head by 1 meter, did your body only expend 500 joules of work? If that is the case, that's really pathetic. Right? Is it true? Well, of course, MGH, that is equal to 500 joules. But that is only the gravitational potential energy gain for the weights. Your body, in order to achieve that, has to do other things. For example, you breathe harder, your body temperature goes up, you sweat. All of these things that's going on in your body requires extra energy. And that's not counted in that 500 joules, don't you think? I mean, think about it. Even if you don't lift anything, you go to the gym, you just walk the treadmill, right? That burns energy as well. You're not lifting yourself up or lifting any weights up. You're not doing any work to anybody, and still you're burning calories, don't you think? Right? When you bring up your heart rate, your heart has to pump harder and faster, and that takes energy. So this number, 800,000 joules, that is a correct number. But that 500 joules of energy expended per lift, that is only a part of the energy your body has to expend per lift. There is extra energy burning. But it does tell us that to get really good effects when it comes to weight control, eating the right portion is important. It's not just how much work you do in the gym. No, you really have to control your appetite as well. Okay, but speaking of the energy burned by your body, there are some good numbers to know. Did you know that in order to sustain life, an average adult will have to expend roughly 100 joules of energy per second? Okay, that is a very easy number to remember, because this is basically saying that to keep yourself alive, it's like burning a 100-watt light bulb. Okay, so the power to keep us alive is about 100 watts, or 100 joules per second. Think about it. This is a remarkably small number. Our body is a very complicated system. Our brain, which is a supercomputer, faster than any supercomputer in the world, and then we have the heart, which to pump blood all over the body, right? And then we have the digestive system. We also walk and all these things. All these functions require energy expenditure. The brain, for example, is a supercomputer, but it consumes on average only about 20 watts. What kind of supercomputer is so lean when it comes to power consumption, right? So it's a very small number, but still, that's 100 joules per second. How many seconds are there in a day? 24 hours. Well, the time in a day, 24 hours, is actually exactly 86,400 seconds. Trust me, you can do 24 times 60 times 60. Okay, and therefore, how much total energy does our body have to consume just to keep ourselves alive, not gaining or losing weight, just to keep yourself alive? This energy, P times T, is 100 watts times 86,400 seconds. It's about 8.64 million joules of energy consumed on a 24-hour basis. And you divide this by 4, you will get number of small calories, and divided by another 1,000, you will get number of big calories. Okay, and if you do so, you divide it by 2,000, 4,000, you get roughly 2,200 big calories. I get about 21 to 2,200 big calories. And this is the reason why the US government recommends that you take in, for the average healthy adult, you take in about this many calories through food every day, 2,200 big calories. This explains why the 200-calorie burger is really just a very lean burger. If you eat only 3 of these lean hamburgers, one for breakfast, one for dinner, and one for lunch, you'll be only taking 600 big calories, but you need 2,200 small big calories to function on a daily basis. So therefore, you're actually losing energy. You'll be losing weight as a fact, okay, as a result. So these numbers actually do work. Okay, going to the gym actually works, but the numbers are, and these are underestimations. They didn't consider other things, only the potential energy of the weights that you lift. All right, now let's continue. When we defined 1 calorie, we talked about heat needed to raise the temperature of 1 gram of water by 1 Celsius degree. Okay, what if you want to lift the amount of 2 grams of water through the same temperature change? You have to give it double the amount of heat, right? So how much heat is needed in general to bring up a certain amount of water, not necessarily 1 gram, and through, let's say, not 1 Celsius degree temperature change, but 10 degrees change or 20 degrees and so on. What is the general formula? Well, clearly, the amount of heat Q that you need to increase the amount of to increase the temperature of water has to do with the mass of the water whose temperature you want to change. It has to do with the temperature change. Okay, do you increase temperature by 1 degree or 2 degrees? It makes a difference. Okay, assuming that the amount of heat you need, increases evenly as you change the temperature evenly, then it would have to do with delta T, the change in temperature. It's proportional to delta T. When you double delta T, you also double the amount of heat that you're taking. Okay, but these are all proportionality. There is a constant that's missing here, and that constant here will turn this proportionality into an equal sign. Okay, what is that constant equal to? We call that constant C here. And with that C, you can then turn this into a equality. Okay, in fact, with that constant, I'm going to rewrite another line with that constant in it. I'm going to turn this into an equality, and that is Q equals to Cm delta T. What is the meaning of this C here? If you move m delta T to the other side, then you get C equals to Q over m over delta T. So what is C? C equals Q if m is 1 unit and delta T is 1 unit, which means this number C here, this quantity C here, is the amount of heat that you need to change 1 unit mass by temperature of 1 degree. Okay, that is called the specific heat capacity, sometimes simply called specific heat. Specific heat or specific heat capacity. And what about, sometimes we talk about heat capacity, not specific heat capacity. Okay, this is specific heat capacity that we just defined. Heat capacity is the same as specific heat capacity, except the mass is no longer limited to 1 unit or 1 gram, such as 1 gram or 1 kilogram. We simply give it any mass. So heat capacity is really just the specific heat capacity times the amount of mass. Okay. So this is the definition of specific heat. So given this definition, what is the specific heat of water? We already know this number, because for water, if you take m equals 1 gram, delta T equals 1 Celsius degree, Q would be equal to 1 calorie. That's how we define 1 calorie. So therefore, the specific heat of water, C water, okay, is 1 calorie per gram per Celsius degree. That's the definition, okay? Or you can also convert it to joules, kilograms, and so on. So you can, for joules, you have, you change this to kilograms, right? Celsius degree. So this becomes 1 kilocalorie or 4,183. That's if you use the SI unit, joule and kilogram. So, okay. Specific heat is a quantity that tells you how much heat does it take to change the temperature of a certain substance. The greater this number, the harder it is to heat up something or to cool off something. Okay, now it depends on what kind of substance we're talking about, and there's a table here for some representative substances. There's some representative solids. Most of these are metals, and then you have also some representative liquids and gas. You look at these numbers. Which number stands out as the largest? Okay. In this table, you clearly find that water has the greatest number of in the specific heat, 4,186 joules per kilogram per Celsius degree. Is this because the size of the table is small, did it include other materials? Well, it turns out that you can include millions upon millions of materials that we have tested, okay? And very few of these substances have a higher value of specific heat than water. Water is the most abundant and common substance on the planet, one of the most abundant common substance, okay? Life on this planet is water-based. Just because water is such a common material doesn't mean the physical characteristics of water are unremarkable. Actually, water has some of the most interesting and unusual behaviors in any substance. And we already saw one example, right? And that is the density of the water is the highest, around 4.2 degrees Celsius. And as you cool off water from that temperature down to 0 and beyond, when water becomes ice, actually expands rather than shrinks. That was a peculiar nature of water, and that's how life can be developed on this planet. Otherwise, like I said, ocean would freeze over during the wintertime, right? And here's another interesting feature of water. Water is one of the most difficult substances to heat up. It takes extra amount of energy to do so, okay, because of the large value of specific heat of water. Now, does that have consequences in real life? You bet it does. Okay. For example, you look at coastal weather versus inland weather. Here in Los Angeles, we can actually see that very clearly. Those coastal cities, their summers are milder. They don't have extremely high temperature, and their winters also milder. They don't have very, very cold weather. Versus if you live inland in a desert, in the summer it's extremely hot. In the winter, it can be very, very frigid cold. And really have to do with the specific heat of water, folks. Because near the ocean, you live on a coast, you're near a very large body of water. And the thing about water is that, it has a very large heat, specific heat, which means that it's difficult to change the temperature of the ocean water. Okay. And when the temperature of ocean water is kept relatively constant, actually not quite constant, but with smaller variation, it can also influence the temperature of the air around you, around the water, to keep the temperature, to keep the weather mild year round. That's one of the reasons people like to live on the coast, because of the mild change in weather. Okay, whereas if in the desert, we're looking at sand, that's a very different substance than water. The specific heat is much smaller. So you can have a large temperature variation on a 24-hour basis, not just for 4 seasons, but 24-hour basis. During the daytime, the heat can the heat from the sun can easily heat up the sand, making the temperature very high and also increasing the temperature of the air. During the evening time, the sand can cool off very quickly without losing a lot of heat, and then bring down the temperature of the air around it as well. All right. But why does water have such a high value of specific heat? That is a story that you will see later when you study the molecular structure of water. It's not something we can easily explain here yet. Now, when you give heat to a substance as at the same phase, which means solid phase, liquid phase, or gas phase, it stays at the same phase unless the temperature goes up too high or too low, right? Between 0 degrees Celsius and 100 degrees Celsius, water stays as a liquid. So as long as you stay at this temperature range, you give it some heat, the temperature will go up. You take away some heat, temperature will go down. What if you cross between two states, say ice melting into water or water evaporating into steam, right? There's what's called a phase change. What happens? Do you require heat to do that? Well, common sense tells us yes. Ice is not going to melt until you give it some heat. For example, drop an ice cube into warm water, it's going to melt because it receives heat from the warm water, and as a result, the warm water becomes cooler, right? And in order to turn water into steam, you also have to heat it up. Right? What happens during the phase change? Okay, when ice melts in water and water becomes steam, what happens to the temperature? Well, let's look at this chart here. It's interesting. It says this, what it depicts is the heat that you need to add to 1 gram of water to change its temperature. Actually, not just liquid water. Okay, we start off here at on this side, you have what is actually still ice at this point. Okay, you for 1 gram of water, in this case, the temperature starts off at negative 30 degrees Celsius, negative 30 degrees. Now you give it some heat. At some point, the temperature becomes 0 degrees Celsius. Okay, during that time, the more heat you add, the higher the temperature becomes, and it's an increasing function of time. Okay, this is an increasing function of time for this region. But once you reach 0 degrees Celsius, right? Once you reach this temperature here, 0 degrees Celsius, you give it some more heat, right? You continue to give it more heat from you give it from between 62.7 joules of heat to 396 joules of heat. During that time, you see the temperature of water stays constant. Look from B. Okay, look at this part B. The temperature of water does not change. In fact, this is when water and ice mixes together. This is when ice gradually melts into water. So during that time, when ice melts, there is no change in the temperature of the ice-water mixture. It stays at 0 degrees until at this point, okay, you give it this much heat, you find all the ice has turned into water at 0 degrees. So during the phase change, there is no temperature change, that's what we observed, but you still have to give it heat. How much heat? For 1 gram of water, it's 396 joules minus 62.7 joules. It's about 333 joules to give to 1 gram of water, to turn it from solid state, which is ice, to liquid state, which is water, at the same temperature, which is 1 degree Celsius. Okay, this is called the heat of fusion. Okay, otherwise known as the latent heat of fusion. Okay, the heat that you need to add or take away from the system in order to change its phase per unit mass is called latent heat. There is latent heat of fusion, latent heat of vaporization, and so on. Okay, now that's a lot, you think about it, right? It only takes 1 calorie or about 4 joules of heat to change the liquid water temperature by 1 degree. And even if you bring the temperature all the way up for 1 gram of water, all the way up from 0 degrees to 100 degrees Celsius, for 1 gram of water, you only need, 100 calories or about 400 joules. But to change 1 gram of ice into 1 gram of water at 0 degrees, you already need 333 joules. of heat. That's a lot. Okay, so you wonder, the temperature didn't change, the phase did change, but the temperature didn't change. Didn't change. What did I give that heat for? How come in order to melt from solid into liquid state, I have to give it this much heat? What is latent heat used for, basically? Right? Well, look, you give energy to the system. The energy to the system will increase. There's no question about it. Okay. In the liquid state, what kind of molecular energy increased as you change as you give it heat? Well, the molecules move faster on average, right? And that is represented as a temperature change. So even though we haven't discussed the details about temperature associated with molecular kinetic energy, you already have some hint from here, and that is, temperature is related to the molecular kinetic energy. But molecular kinetic energy is not the only form of internal energy. Remember, molecules always also interact with each other with a force, and there is a potential energy with them as well. Different states have very different molecular motion. For example, in the solid state, the molecules are tied together very tightly, so they cannot move away from each other. The shape doesn't change. But in liquid state, the connection is much looser, and therefore, they cannot hold on. Liquid cannot hold on to a definitive shape. In a gas state, it's even worse. Molecules simply fly away from each other. So there is a much looser connection between molecules as you move from solid to liquid and then to the gas state. As you break the connection looser, you have to give it energy. It's initially they're tied, just like the Earth and anything on the surface of the Earth. The Earth attracts it, right? Give it a negative potential energy. If you want to break that bond, you want to send something away from the Earth, escape the Earth's gravity, or you have to give it energy, right? So therefore, this is what latent heat is used for. It breaks the molecular bonding from one state to another, give it smaller, looser connection from solid to liquid or from liquid to gas. And breaking a bond requires energy. Okay, so that energy, that heat, latent heat going in is used to increase the molecular potential energy to break the bond instead of changing the kinetic energy. Okay, once it reaches a certain state and the state doesn't change anymore, it stays liquid or stays as gas, then the heat that you further introduce will now change the kinetic energy, which then means the temperature will change. Okay, so look at, let's continue with the table here. You now will have a liquid state, So it's between here and here, right? And the temperature goes up from 0 degrees to 100 degrees. This is when water stays as a liquid, and the heat that you bring in will increase its kinetic energy, so the temperature rises. And how much heat is needed? Remember, we're looking at 1 gram of water, right? So the temperature changes by 100 degrees from 0 to 100, and you need to give it 100 calories, or about 400 joules of energy, as is indeed true. So from went from the energy intake went from 396 joules to 815 joules. Okay, now once it reaches a 100 degrees, so we're looking at the boiling point of water right here. Next, if you keep on giving it more energy, water is now ready to turn into steam, into a gas. So we're talking about a large increase in intermolecular potential energy, because between liquid and solid, there is a potential energy change, but not by much, because still the molecules stay close together. They're still attracted towards each other. But once you take the liquid state and turn into a gas, the density dramatically decreases. The water will expand by many times in its volume. And so we essentially broke the entire bond between adjacent molecules, and that takes a lot of energy. Okay, it's not like lifting a person from the ground to the top of a skyscraper. You're taking a person from the ground all the way to the moon. It's a huge amount of energy difference. So therefore, it makes sense to imagine that taking 1 gram of water taking 1 gram water and turn it into steam requires a whole lot more energy than taking 1 gram of ice to turn into 1 gram of water. Okay? So the latent heat of fusion should be considerably greater than the latent heat of, the latent heat of vaporization, I should say, should be much greater than the latent heat of fusion. And that is the case for water. For 1 gram, you have to give it a whole lot more energy between this number and that number to complete its phase change between liquid and gas state. Okay, the latent heat of fusion for water, if you use calories, 79.7 calories per gram for water. But the latent heat of vaporization, here you can read it from this diagram, which is in joules. This number minus that number, right? But in calories, 540. You can do the conversion yourself, and that's much greater than 79.7 calories per gram, which makes sense. Okay, now once it reaches a point E and all the water has to be turned into steam, if you give extra amount of heat, now it stays at the gas state. The only thing it will do to increase its energy. Increases temperature, you give more energy. And that has to do with the specific heat of steam. Okay, so this diagram tells you what happens to the temperature when you give more and more heat to 1 gram of water, and basically you're looking at heat needed to change its molecular kinetic energy and heat needed to change its molecular potential energy.